Hello friends, in previous lecture we have talked about the convergence and divergence of the series of real numbers, and we have studied the necessary condition for convergence of real numbers, convergence of series of real number. That is, if summation of n is convergent series, then limit of nth term an must be 0. So an approaches to a 0 as n tending to infinity. So we'll take the algebra of convergent series theorem. If summation of n equal to 1 to infinity and summation of bn n equal to 1 to infinity converges to a and b, converges to a and b belongs to R respectively, then 1 summation of n plus bn, addition of series, converges to a plus b, and second summation of k times n equal to 1 to infinity converges to AB, k into b, k into a, sorry. That is summation of n plus bn, okay, is equal to summation of n plus summation of bn. That is summation n plus bn equal to summation an plus summation bn. And here summation of k times an is equal to k into summation an. Okay. We will prove this result by using definition of convergence of series. So here given summation an equal to 1 to infinity is equal to a, summation bn n equal to 1 to infinity equal to b. So let Sn is equal to a1 plus a2 plus dot dot up to an, tn is equal to b1 plus b2 plus dot dot up to bn for every n belongs to n. Then Sn, this is 1, this is 2. Then Sn and Tn are sequences of partial sums of summation an and summation bn series bn n equal to 1 to infinity series respectively, right? By 1 and 2, first by 1 and 2 limit n tends to infinity of Sn is equal to a limit n tends to infinity of Tn is equal to b. Therefore, limit n tends to infinity of Sn plus Tn is equal to limit Sn plus limit of Tn equal to a plus b. Where Sn plus Tn is a sequence of partial sums of series summation of n plus bn. summation an plus bn, n equal to 1 to infinity, right? And therefore by 3 summation of n equal to 1 to infinity an plus bn converges to a plus b, that is summation an plus bn n equal to 1 to infinity equal to a plus b, but what is a is nothing but summation an and b summation bn n equal to 1 to infinity, right? Second, now summation of n converges to a if and only its sequence of partial sum Sn converges to a, and therefore limit of Sn is equal to a. Therefore limit of scalar multiple sequence is k times limit of that sequence ka, where Ksn for k belongs to R. For any k belongs to R, where Ksn is sequence of partial sums of series summation of Kn n equal to 1 to infinity, right? Therefore by 4 summation Kn n equal to 1 to infinity converges to Ka, that is summation Kan n equal to 1 to infinity, this equal to Ka, which is same as k into summation of An. So addition of two convergent series is again convergent, and that series of addition terms converges to sum of that two series. Similarly, scalar multiple of series. Okay. If summation of n converges to a, then an is a sequence of real number. For that, k times an is scalar multiple sequence, and corresponding series summation of k times an must converge to k into summation of an, where k is any scalar. So this is about the algebra of series. Now here summation of n converges to a, summation of bn converges to a, then summation of n minus bn also converges to a minus b, because I can write summation of n plus bn as n minus bn as summation of an plus minus bm, and then it is nothing but summation of an plus summation of minus bn, and then I will take minus 1 outside from it. So series of difference of terms of the given two series converges to difference of that two sums. Okay. Now we'll take a few examples from exercise 3.1 board work. Exercise 3.1. In that first example is that prove that if a1 plus a2 plus a3 plus dot dot etc. converges to a capital A, then a2 plus a3 plus a4 plus dot dot etc. converges to a minus a1. Okay. One, I can take here also a2 plus a3 converges to that. Additionally, b plus a1 plus a2 plus a3 plus dot dot etc. converges to a plus b. So in given series, convergent series, if you delete few terms of that series, then resulting series is also convergent and it converges to original sum minus sum of the deleted terms. In addition that, in convergent series, if you insert few terms, then sum of that convergent series will be increased by sum of that added term. This is the meaning of this result. So solution. So given summation of n equal to 1 to infinity equal to a. Let Sn is equal to a1 plus a2 plus a3 plus dot dot up to an for every n. Then Sn is sequence of partial sums. Sn is sequence of partial sums of series summation an. Therefore, by 1 limit n tends to infinity of Sn is equal to a. Here n equal to 1 to infinity. 1. Now for series a2 plus a3 plus a4 plus dot dot etc. is equal to summation of ak, k equal to 2 to infinity. Tn is equal to a2 plus a3 plus dot dot etc. up to an plus 1. An plus 1. Then Tn is sequence of partial sums of series summation ak, k equal to 2 to infinity such that Tn is equal to Sn plus 1 minus a1 for every n. Therefore, limit n tends to infinity of Tn is equal to limit of Sn plus 1 minus a1, which is equal to limit of Sn plus 1 minus a1, which is nothing but a minus a1 by 2. If Sn converges to A, then its any subsequence converges to A. Sn plus 1 is subsequence of it, so it converges to A. Is it right? So, which is equal to limit of Sn plus 1 also, right? So, you get this. This implies summation of a k equal to 2 to infinity converges to a minus a1, that is summation a k equal to 2 to infinity is equal to a minus a1. Okay. Second, for series b plus a2 plus a3, a1 plus a2 plus a3 plus dot etc. T1 is equal to 1, T1 is equal to b, and Tn is equal to b plus a1 plus a2 plus dot up to an minus 1 for every n greater or equal to 2. For every n greater or equal 2, okay, which is equal to b plus Sn minus 1 for every n greater or equal to, okay, by 2. Therefore, limit n tends to infinity of Tn is equal to limit of b plus Sn minus 1, which is equal to b plus limit of Sn minus 1 is equal to b plus a, since limit of Sn is equal to limit of Sn minus 1 is equal to a, right, where Tn is sequence of partial sums, of series b plus summation of a k equal to 1 to infinity, and therefore b plus a2 plus a1 plus a2 plus a3 plus dot etc. converges to b plus a, right. So, in convergent series, from convergent series, if you delete few terms, here we are proving result only for one term, but result is true for any number of terms, finitely many terms. So, if you delete few terms from the convergent series, then that new series converges to sum of original series minus sum of the removed terms. While if you add few terms in given series, then sum of that new series will be increased by sum of that added terms. Only this is the part of this example. Next example, for what values of x does the series of x does the series 1 minus x plus x minus x square plus x square minus x cube plus dot dot etc. converges. Okay. Solution for series 1 minus x plus x minus x square plus x square minus x cube plus dot dot etc. Sn is equal to 1 minus x plus x minus x square plus x square minus x cube plus dot dot etc. plus x raised to n minus 1 minus x raised to n minus x raised to n. You can observe here these intermediate terms get cancelled and we will get Sn is equal to 1 minus x raised to n for every n. For every n. Okay. What is the limit of this? Now, limit n tends to infinity of Sn is equal to limit n tends to infinity of 1 minus x raised to n, which is equal to okay. 1 minus 1 is equal to 0 for x is equal to 1, for x is equal to 1. Then 1 minus 0 is equal to 1 for mod x less than 1, mod x less than 1. Is it clear? And this x raised to n goes to infinity for x greater than 1, for x greater than 1. Okay. So it is 1 minus infinity is equal to minus infinity for x greater than 1, x greater than 1, and doesn't exist if x is less than equal to minus 1, x is less equal minus 1. Okay. Doesn't exist for x less equal minus 1. Therefore, given series, series 1 minus x plus 1 minus x square, x minus x square plus x square minus x cube plus dot dot etc. is convergent if minus 1 less than x less equal 1 and 1 minus x plus x minus x square plus dot dot etc. is equal to limit of Sn. This is equal to 0 for x is equal to 1 and it is 1 for mod x less than 1, that is minus 1 less than x less than 1. Minus 1 less than x less than 1, we will get this. So, with this example, we will stop our session here. Thanks for listening lecture carefully.